All right, welcome. My name is Ryan Holger. I'm with Temperature Equipment Corporation. This week's webinar is really a follow-up to one that we did in January. So if you're not aware, we did a webinar in January on the IECC 2015, both residential and commercial with an HVAC focus. That webinar is recorded and is available on our website for those of you that have not seen it yet. It's tecmungo.com. And then click on training and then I think online training, and you'll get there to see that. This week's topic is a follow-up to that, and we're going to stay on the commercial side of the equation, and we're specifically going to focus on control systems and things that are directly related to controls. We did this exact presentation for the ASHRAE chapter meeting a couple weeks back, so I figured why not do it for the whole state here if we can. So what are we actually going to be covering today? Oh, let me also say that this is a PDH webinar. And as you guys know from past PDH webinars, you do need to answer the quiz questions when they come up and answer them correctly. I believe there's 7 questions and you need to get 5 of them correct. So please do pay attention and make sure you answer those. So what are we specifically going to cover? Well, we're obviously going to talk about the IECC. That's the big elephant in the room, the big thing that's changed in the past couple months here. We'll also talk about some other standards and codes that relate to HVAC control systems. But the bulk of our time will be spent on the energy code commercially. We'll talk a little bit about energy standards, we'll talk a little bit about mechanical codes and standards. We'll tie in a little bit of lead discussion, ASHRAE 15 for refrigeration, at least as far as the controls perspective, thermal comfort standard, F55, Chicago code. We'll try to get a little splattering of everything in there. We won't be able to do everything, obviously. Each one of these topics could be a full 8-hour day, and I only have an hour with you guys, so I'll try not to bore you too much. Everything we talk about today is going to assume that whatever code or standard we're talking about, we're doing the prescriptive method of compliance, which means it says something in the book, you do that something, and you are fine. Some of these standards and codes have performance-based compliance methods. We are not going to talk about those today, just so I'm letting you know before we get all those questions on that. So as you know, statewide, you're required to file the International Energy Conservation Code. We've been doing this commercially since the 2006 version, residentially since 2009. We just switched to the 2015 on January 1st, 2016. And currently, we are on an automatic 3-year update cycle, which means theoretically, 3 years from right now, we'll be on the 2018 version. There are some lawmakers that are thinking about changing that so it could work a little differently in the future and only auto update if a certain percentage improvement is achieved. But for right now, every 3 years, you got to do it. Right? So we went live 2 months ago. Well, actually, almost 3 months ago now. So if you're not following the current IECC 2015, you are, in fact, behind. We are one of just a few states that have already jumped on board with it. The ones in green are those states. I think we were probably the 3rd or 4th one. But as you can see, we're the first one here in the Midwest. So we don't have a lot of our peers to look towards for interpretations. So a lot of the interpretations are being done at the state of Illinois from the Energy Office and kind of winging it that way. I should say winging it, kind of evaluating it that way. But as more states come online with it, you'll see that change. So green is on the current 2015, blue is on the quote-unquote old 2012 code, and then yellow is even older, and white is the wild, wild west. They don't even have energy codes. This is the state website. Normally I would not talk about this, but I get so many questions and people asking me to prove to them that there really is a state code. Sending someone to this website has been the easiest way to do it, ildceo.net/energy code, and it'll specifically tell you right there that we are on the 2015 and that we have amendments. And if you click on that word highlighted in yellow, Illinois amendments, you will get the 10 or 12 pages of things that have been tweaked in Illinois, the majority of which are residential. There are a few commercial things in there. City of Chicago is another one that everybody says, oh, Chicago has their own energy code. Well, Chicago does have its own energy code, and you have to comply with the Chicago Energy Code. And you also have to comply with the state energy code, IECC 2015. And the City of Chicago Building Permits website specifically states right there in yellow that you have to do both. So whichever one is more stringent, you have to do. If one of them tells you need economizers for 54,000 BTUs and up, and the other one says 33,000 BTUs and up, guess what? 33,000 BTUs and up, you got to do it. So you got to comply with both codes because your life wasn't complicated enough previously. So like I said, we're going to stick on the performance compliance paths. We're going to skip all the ASHRAE 90.1 compliance path discussions because they are very similar to the IECC. But as you probably know, if you comply with ASHRAE standard 90.1 in its entirety, you automatically comply with the IECC 2015, even if you've never cracked the book open. So one way to comply with the IECC is to do 90.1. You cannot do that on a pick and choose type thing. You got to do the whole entire project that way. Lighting, envelope, HVAC, the whole 9 yards. You can't just say, oh, for this one little thing, the chiller, I'm going to do it the other way. The whole project has to go 90.1 or the whole project has to go IECC. Once you choose the IECC method, you have two ways you can comply. One is prescriptive. Like I said, you do whatever the book says you have to do and you're done. Or the other is a performance-based one. You have to do some mandatory sections as it lists there, 4025, 4032, etc. And then you got to do an energy model on the building against a reference building, and you got to beat it by 85%. So if you do the performance-based method, you got to do better than code. But some projects prefer to do it that way because they want to trade off certain things, have this kind of window versus this HVAC or whatever they want to do. So we're going to stick on path number 2 here for today's purposes to kind of simplify the whole discussion. The very first thing we're going to talk about from a controls perspective is outdoor air economizers. Why are we talking about that first? Well, we're talking about that first because that has the vastly largest number of changes for this year. There are 3.5 to 4 pages of economizer related language in the IECC 2015. And it's not in a section called Economizer. It's scattered in all kinds of different sections. So I grabbed some of those sections out today and I'll try to show them to you. But different things that you have to do on Economizer are hidden in different spots, and it's kind of weird. Hopefully no one from ICC is on the webinar and heard me call them weird. So if you didn't know, an outdoor air economizer is used for free cooling. At a residential house, if you want to get air conditioning in Chicago or Illinois in the middle of the winter, you probably don't turn your air conditioner on. You probably just open a window, right? Well, the problem with most commercial buildings is they don't have windows that can be opened. And even if they do, people don't open them at the right time, right? Operable windows is very challenging to get people to do what they're supposed to do. So instead, we put an operable window inside your air handling piece of equipment or your rooftop unit. And whenever we want to cool the space and it's cool enough and or dry enough outside, we will open that window and suck fresh air into the building to free cool it, hopefully without having to even energize any compressors. We'll talk about that. There are 3 main ways that we control this, specifically in our region of the country anyway. The first of which is dry bulb temperature. For those of you guys that have seen my economizer classes before, you'll notice that over the years that OA less than 70 degrees Fahrenheit number has gone higher and higher every time I do the class. 15 years ago I used to say 55 degrees, and then I got smarter and picked a new number and smarter and picked a new number. And now because of the code, I have to pick 70. Normally, up until last year, I was picking 65, which I thought was pretty aggressive. The code actually requires 70. So what does that mean? That means if you want to cool the space and the outdoor temperature is below 70 degrees, then you would open up the outside air damper and use the outside air to cool the space. Now, I know you can't cool most spaces with 70-degree air, but 70-degree air is probably better than whatever was going to come up the return duct, right, which was probably 75 or 78-degree air. So it's still better. So it'll help cool it some, and then you might have to have compressors assist it later on. So for you guys that do field work, by code, you're required to set all the economizer changeovers for 70 degrees. If you're still doing it for 55, you are woefully out of compliance for this code and for the previous versions of the code. The second way you could do it would be enthalpy, right? For those of you that don't know what enthalpy is, don't even use the word enthalpy. Just think of temperature and humidity. We're going to check both things, and if one of those things is quote-unquote bad, we're not bringing the outside air in. So if you do an enthalpy-controlled economizer, instead of a 70-degree set point, the code will require a 75-degree set point, right? A little more aggressive. But we're also going to check to see if the humidity is high or low. So if the humidity is low and it's less than 75 degrees, yeehaw, economizer time. If the temperature's high or the humidity is high, forget it. We're not doing it at all. Right? So enthalpy economizers allow us to do a few more hours a year of economizing because we're being smart and checking the humidity too. Differential enthalpy, which would be the third type, is just like regular enthalpy, except I'm going to look at the temperature and humidity of the outside air, the temperature and humidity of the return air, and I'm going to decide who's cooler and drier, and whichever one is cooler and drier, I'm going to use that airflow stream, right? Because air going through my supply fan can only come from one of 2 places, the outside air lever or the return duct. So if I want cooling, and I only got 2 places to pick it from, Whoever's cooler and drier, I'm going to take that airflow. And then I'll just use the compressors to supplement that as needed. So it wouldn't be a PDH seminar if we did not have a psychrometric chart involved. For you guys that aren't familiar with psychrometric charts, don't freak out. Hopefully you can see my pointer mouse thing here, right? So the psychrometric chart on the bottom scale, that is your dry bulb temperature from left to right, going low to high, 30 to 120 in this case. Up the vertical scale is your indicator of moisture content. The curved lines going all the way through the graph here are your relative humidity, right? It's relative humidity because it's not direct humidity like over here. It's relative to how warm the air is. So if I was to set your economizer for 55 degrees, that's this black line over here, the black dotted line, right? Anything to the left of that line would have been an economizer day, and anything to the right of that line would have been a compressor day. Now I'm going to move that line over to where the yellow one is at 70 degrees, right? So everything in between there, those 15 degrees of outdoor temperature on the bin chart are now available to me for an economizer mode, right? So a dry bulb is pretty straightforward. I got a 70 degree set point. I got a temperature sensor. If it's below 70, economize. If it's above 70, compressors. All right. We'll talk about integrated economizers here in a second too. For right now, we'll just hold off on that. If I have an enthalpy economizer, then what I have is this angled, let me get my pen back out, this angled yellow line here, right? So I'm looking at enthalpy, which is temperature and humidity combined. And if you're familiar with the psych chart, these lines over here on the left are my enthalpy lines. So right now I've set this guy for 25 BTUs per pound of dry air for my enthalpy, and that line goes across like that. But I don't want to take a day where it's 95 degrees out just because it's dry. That's way too hot. So I also have a temperature cutoff, in this case by code of 75. So if anything's below the horizontal or below the angled line and to the left of the vertical line, this whole region over here that I just circled, that's going to be my economizer day. And everything over here with the red arrow on it, that's going to be my compressor day. So I'm getting a little bit more in this shaded area that I'm making here. I love this pen thing. I know you guys probably hate it when I do it, but I love it. That shaded pen area there is more economizer days that I didn't have before. This shaded triangle over here is days I'm not going to run the economizer because it's too humid, and I shouldn't have been doing it to begin with. I just never had a sensor until now. A couple of things on economizers too. We have to do an integrated economizer. That's required by code. I'll show you the language requiring that here in a second. Integrated economizer means that you have to have the ability to run the compression in conjunction with the outside air for cooling. So it's kind of like first stage is use the outside air. If it's cool enough, use the outside air as your first stage of cooling. If I still need cooling, real quick, I apologize, guys. Somebody's typed in that they don't have any sound. Does everybody else still have sound? And is Steve the only one? Or are you guys all host? Okay, everybody's telling me they got sound, so Steve must have a particular issue. Steve, I would suggest maybe you switch over and try it on the telephone versus the computer speakers or vice versa if you're having an issue. I'm going to keep moving on for everybody else right now, and it is being recorded, Steve. Not that Steve can hear anything I'm saying because he has no sound, so never mind, Steve. I guess I didn't think of it like that. Integrated economizer means I'll run the fresh air cooling along with the compressor cooling as needed. Economizer is my first stage. If it's good outside, compression is my second stage. Right? So I need to do that. It's required by code to do an integrated economizer. I also have to figure out how I'm going to get air out of the building. If I'm going to open up this window with a fan on it and suck all this extra outside air in to cool my building, well, I'm going to pressurize the building. Where's all that air going to go? It can't just stay in the building, right? Otherwise, my building will blow up like a balloon, which it's not going to do, obviously. So if I do nothing and I run an economizer, I'll end up blowing the front doors wide open, and it'll be difficult to shut them and all that kind of stuff. So I have to have a pathway to get the air back out of the building. There are numerous ways that we can do that. We could do it with a barometric relief damper. We could do it with a motorized damper and powered exhaust fan. We can do it with an external exhaust fan that's outside of the air handler or rooftop. We could do it with a dual stage relief path. There's lots of ways we can do it. We could talk all about that stuff if you guys want to later. But just make sure you have a plan on getting air back out of the building because they're going to suck a lot of air in. The one that gets everybody, and this is not even new on the 2015 code. This came in the 2012 code. It just wasn't being policed until more recently. The economizer also does double duty and serves as my minimum mechanical ventilation code intake, right? So I need 10, 12, 15, 30% outside air by code for whatever my project needs. I typically bring that in through the economizer damper. Let's just say 30% for argument. And then if I have an economizer cooling day, I modulate between 30 and 100% open. But that first 30% comes on whenever the building's occupied, right, to bring fresh air in for the people. The problem is that a normal packaged rooftop unit opens the economizer to its minimum position whenever the fan is on, because it doesn't know anything else. So that means if your rooftop unit turns on in the middle of the night for setback heating or cooling, which it's definitely going to do, and the fan turns on, which it's definitely going to do, you open up the ventilation damper and you suck in 20 or 30% outside air to ventilate a building that has no people and does not require any ventilation during that time period per code. Right? It's a huge, huge energy waster, and it's very easily preventable. Every single economizer controller put on every single rooftop, at least in the past 8 years, if not longer, has an input on it for occupancy. It's got 2 terminals there that are labeled occupancy typically, and it's saying, put a time clock on me. Tell me when I'm supposed to be on and when I'm supposed to not be on for ventilation. You could put a separate time clock on there, but honestly, no one would ever look at it or change it. So really what you want to do is use a thermostat that has an extra spare output on it, and that output from the thermostat will go up to the economizer controller and tell the economizer whenever the thermostat is in an occupied mode. And we'll do ventilation then. And if it's unoccupied, we won't do ventilation. And if I can cut back 20 or 30% of your outside air every time the fan turns on all night long, it's a huge energy savings. We've been lobbying for it for years, and it's actually code required now, so it's not even like you have a choice. This will significantly change the thermostat choices you have. It won't really affect the economizer choices because the economizers all can do it. But there's only probably 25 or 30 models of thermostats that do this. So if you need help with that, let me know. I'm not going to read every single code section to you guys because that would be boring, and hopefully you all have a code book. If you don't have a code book, you need to get one for sure. It's ICC safe, SAFE.org. You can buy the books on there. I think it's like $45 or $49. It's not a deal breaker. But I will highlight some of the sections. This is the specific section that says when you need an economizer, and specifically for us in climate zone 5A, which is Chicago and the suburbs and so forth, where most of you guys are from, 54,000 BTUs and up is when you have to have an economizer. So this is 4.5 tons basically and up. This is not just for rooftops. This is all cooling systems. So if you got a split system, if you put a residential furnace and condensing unit in a commercial building, guess what? If it's 4.5 or 5 tons, you got to put an economizer on that split system. This is less stringent than the old number, which was 33,000 BTUs. So this new one went up a little bit, so you don't have to do it in quite as many scenarios. So now it's 4.5 tons and up, basically. There are some exceptions to that. They're not a big deal. Most of them are related to either process applications, like note number 3, residential high-rise buildings, like note number 4, or churches, like note number 5. Those are the ones that will typically come up for you. Pretty much everything else you're going to have to do it. Process, hardly ever use spaces like a church area or a high-rise residential. You won't have to do it. Everybody else is probably going to be in a scenario where they got to put an economizer on their rooftop, on their split system, on their fan coil, on their air handler, on their water source heat pump. It doesn't matter. If it does cooling and it's 54,000 BTUs, it has to have an economizer. This is our geographic map, which I should have probably put up a slide ago, but I mixed it up, I guess. We are climate zone 5A currently. 5 is the whole green section for you guys that are in Chicago. My friends in Wisconsin that are tuning in, you guys are 6A typically, unless you get really far north. But you can look at this map, and this applies to not just economizers, but all kinds of sections in the code. So you need to know what climate zone you're in. A is to the right of that line, B is to the left, and then the far, far Pacific coast is marine, which is C. So we're 5A for most people on this webinar, 6A for a few others, and most of the 5A and 6A stuff is the same. And we did hear a rumor on Friday from a very good source that the entire state of Illinois will likely go to climate zone 4 at the next code cycle, and Wisconsin will go to 5. And most of these are going to be bumping up for all the other states too, due to the global warming effect based on the weather data history. So that will affect what you do, but that's 3 years down the road, so don't choke on it. Next thing on economizers, like I said, is you have to have an integrated economizer. Anytime you have an economizer, it's required to be integrated. So why they made a separate section for it and didn't just list this language in the regular economizer section, I don't know. But if you have an economizer, it's got to be integrated, which means you have to have the ability to run the compressor in conjunction with the economizer damper for free cooling. which means that no matter what, you have to have a two-stage thermostat. Even if you have a one-stage DX system, you need to have a two-stage stat. That is a dead requirement to make this actually work. There are a few other things that are listed on here in the integrated economizer section that have nothing to do with economizers, such as note number 2 and number 3 below. So we will come back to those later on. Why they're in the economizer section, I have no idea, but nonetheless, we'll come back to those in a few minutes here. If you have an integrated economizer, our psychrometric chart looks a little bit different, right? So the blue area on the left, below 55 degrees, I can get it all done with free cooling, right? If I'm trying to get 55-degree discharge air and I got 55-degree outside air available, I should be able to get it done. Maybe a couple degrees for fan heat, but conceptually I got to get it done. If it's really warm, 75 degrees outside and above, I'm probably going to have to run compressors and shut the economizer off. And if I'm in that middle area where the white arrows are at, between 55 and 75, I'm probably going to be in integrated economizer mode, which means I'm trying to do it with the outside air damper, but if that's not cutting it, then I'll engage the first stage of compression to help me out. Mark types in a question, why wouldn't you want to use an economizer on a rooftop that is less than 4.5 tons? You probably would, Mark. In our climate zone, you would, but you're not required to. And I don't know the exact history of why this just increased from 33 to 54, but personally I believe it's because of the small split systems, not because of the rooftops. Because remember, this rule applies to everything. And if you want to put in a nice 95% efficient furnace in a small office building here with a split residential condensing unit, to put an economizer on a residential split system, you got to buy and or build some kind of economizer box with your own dampers and field install your own controls. And it ends up being like $1,200 adder to a furnace that probably barely cost that. So it wasn't really practical for the cost-wise practical for those small non-packaged systems. But yeah, Mark, if you got a rooftop unit and you got a 3 or 4 ton rooftop unit, I would still put an economizer on it. It'll pay itself back in that scenario. But on a split system, maybe not. All right, from a code perspective, this is the specific table that applies to us. We are climate zone 5A in Illinois, 6A for the southern Wisconsin folks we were talking about. So like I said, the cutover point is 70 degrees now, which is higher than it used to be if you have a dry bulb. If you have an enthalpy, it's 28 BTUs per pound of dry air and 75-degree cutoff that you would use. And then differential enthalpy, it's basically whichever one's better, return air or outside air. And then you also have a hard cutoff on the outside air. So that table is the same as it's always been, just the numbers have gone higher to increase the amount of economizer days that we run. The really big change on economizers, and then we'll get off economizers, I promise, it's just there's been so much stuff on the economizer side, is that there's a new section that requires the economizer to have fault detection and diagnostics. And it has its own acronym, FDD, and you know if it has an acronym, it's the real deal, right? It's a real HVAC thing if we assign an acronym to it. It's a big, long section, it's huge. I'm not going to read through it to you. But basically, your economizer controller has to have the ability to detect all kinds of problems that it could have, such as a problem with the temperature sensor readings, the economizer not opening when it's supposed to be opening, the economizer not shutting when it's supposed to be shutting, damper blades getting stuck, too much outside air, things like that. So I got to monitor this thing, and if I have a fault, I have to determine that fault. And specifically, let me get my John Madden pen back out, right? Specifically, the hang-up is being this one right here, number 6. I have to report the faults to a fault management application accessible by day-to-day operating or service personnel or enunciated on a local thermostat, right? So if I got a DDC system and I'm going to text or email alarms out to people, great, done, no problem. If I got a simple job that has a 5-ton rooftop unit with a thermostat, what the hell am I supposed to do, right? So first thing is you're probably not going to be able to use any of the old economizer controllers that you used to use, right? Stuff that you were using for the past decade does not have the ability to monitor any of this stuff. Most manufacturers use Honeywell controls. Honeywell has one controller that does this. It's the Jade controller. By the way, Honeywell 2 years ago announced they are stopping manufacture of all economizer controllers, even for replacement part purposes, and they're only going to make one, which is this Jade controller. So the Jade is what you got to use anyway down the road, unless your manufacturer has their own controller, which is fine. But if you're using Honeywell stuff, then you got to have a Jade controller on all projects, on all rooftop units, on all air handlers with economizers. And then you need to have a thermostat that has an input on it where the Jade can send an output. The Jade will track these same alarms we're talking about here, all of them, and it'll close a contact closure to send a signal down 2 wires down to your thermostat, and your thermostat has to have an input that picks up that signal and then enunciates it on the front of the stat. There are stats from Honeywell that do that, obviously. There are stats from Venstar that do that, and I'm sure there's probably other ones out there as well. But you definitely have to do that. Dale types in a question, and please keep the questions coming in. I'll glance over them every once in a while. Dale's question is, where would the FDD responsibility lie? With the manufacturer or the controls contractor? Also, does this mean package controls are inadequate? So that's a good question in general. So all this stuff in the code, the entire IECC code book, is not the responsibility of the equipment manufacturer to comply with. And I'm probably saying, oh, Ryan's saying that because he works for a rep firm, right? I'm saying that because every single state is different, and the manufacturer makes all kinds of equipment, many of which you can't even use in the state of Illinois. If you guys are on the January webinar, every single package rooftop on the entry level from every single manufacturer, you can't use in Illinois anymore. You have to go up to the mid-tier or high tier to comply with the code just for rooftop efficiency. So the manufacturer is going to make all kinds of different stuff for purposes of all different states and cities and municipalities that have different codes. So they're still going to make stuff that doesn't comply with Illinois. In regards to responsibility for compliance, whoever is pulling and signing the permit, that would be my initial statement in general. If it's a big plan and spec job and there's a professional engineer involved, professional engineer has to make sure that everything complies, or at least he has to tell people to comply, and hopefully they actually do it, right? If it's a small little rooftop change out from just a service contractor, an HVAC contractor, and they're changing a rooftop out, whoever goes down to the city office and fills out the permit application, that person needs to make sure that it complies. The controls contractor, assuming you have a DDC system, he may or may not be responsible if the guy pulling the permit has outsourced the controls to the controls contractor and put in his contract to do certain things, then he would have to do those certain things, obviously. So the ultimate responsibility is whoever signs the permit and stamps drawings. Those are the people. But obviously you can sub some of those responsibilities out as needed depending on what you're trying to do. Sorry for the side tangent. I just thought it was a good question. So now I get to ask you guys a question. So our first quiz question, remember, if you need PDH hours, please answer the questions. I hate it when I get calls from people saying, oh, I didn't answer the questions. Can I still get a certificate? No, you cannot. All right, so question number one, I'm going to launch it right now. What is the current statewide Illinois energy code? And please read all the choices before you click on one because you can't undo your click. Right? So choice number one, ASHRAE 90.1 2010, ASHRAE 90.1 2016, IECC 2015, IECC 2016, IECC 2012. So I will give you guys 30 seconds or so to answer that while I take a drink of water. Looks like 90% of the people voted, so I will give it another couple seconds here, and I will close it in 5, 4, 3, 2, 1. And let's see if we can share the results with you guys. You can see that on your screen. 95% of you got it correct. It is the IECC 2015. I'm surprised no one picked the ASHRAE ones. Usually somebody picks those. And then I actually kind of shocked everybody. 4% of people picked 2012. But all right, so we'll hide that and we'll keep moving on with the topic. So other stuff related to the control system, directly or indirectly. I mentioned there was some stuff in that integrated economizer control section that had nothing, in my mind, to do with integrated economizers or economizers in general. So specifically those couple of things. Note number 2, if you have a direct expansion system that is 75,000 BTUs and up, so 6.25 tons or greater, and the capacity is directly based on occupied space temperature, you have to have no less than 2 stages of mechanical cooling capacity. So basically you got a rooftop unit or an air handler or a split system that is controlled off of a single zone thermostat, you got to have 2 stages. You're not allowed by code to put in a 7.5 or 10-ton single stage unit. I don't know why you do that anyway. It's pretty stupid in terms of load management control, but people do it all the time. I can't tell you how many times I've seen 10-ton rooftop units that are single circuit, single compressor. So you got to have 2 stages of cooling minimum on anything with a space temperature control thermostat. The other one, which is significantly more interesting to me, is note number 3, which is on DX units, once again, whether it's controlled by space temperature or other means. If you modulate the airflow to the space, you need more stages. So what does that mean, modulate the airflow to the space? To me, that means if you got a zoning system, right? If you have a VAV, dampered zoning system, or VVT or other constant volume zoning system, a Honeywell 3-zone panel or whatever it is, if you have systems that throttle the airflow back in order to control the comfort in the space, in those scenarios, you have to have more stages of heating and cooling. So specifically, 65,000 BTUs, which is what, a little more than 5 tons. So we'll just say six tons, 5.5 tons. You have to have 3 stages of cooling. And if it's even bigger, 240,000 BTUs, which is a 20-ton unit, you are required to have a minimum of 4 stages of cooling. So I know that's not the controls guy's problem per se, right? Whoever's doing this controls work. But as soon as you put a zoning system on there as the controls guy, you should be telling whoever's doing the mechanical equipment, hey, dude, I need to have 3 stages or 4 stages. Otherwise, we're not going to, as a group, get this thing to comply. It obviously makes sense. The more you want to throttle the airflow back, the nicer it would be to stage down the mechanical equipment to accommodate that. I just put in a 5-stage condensing unit at my house this fall, so I haven't really seen it run yet. I will in the summer. But it's got 5 stages, and I'm doing that at my house. And I know lots of people have done that at their house. So it's not like it's impossible to get 3- and 4-stage equipment commercially. It's certainly doable. But it will cost more than 2-stage equipment, obviously. Another interesting rule that specifically comes in when we're talking about VAV airflow systems and VVT zoning systems, as well as hydronic fan coils. The way this is worded is so weird. The section itself is labeled hydronic and multiple zone HVAC systems. So anything that's hydronic, meaning it has a chilled water coil or a hot water coil, and anything that's non-hydronic that has multiple zones, so a dampering system. Those two fall into this scenario. You have to have the ability, if you have a 65,000 BTU system or larger, you have to have the ability to stage the fan down as well as the cooling system, right? So I go back here, 65,000 BTUs, I got to do 3 stages of cooling and at least 2 stages of fan. I got to throttle the airflow back at least 1/3. So there's been similar versions of this in 90.1. It's finally made its way into IECC. I'm told that this was supposed to apply to everything, but unfortunately they stuck it under the hydronic and multiple zone subsection, so it doesn't apply to everything yet. But expect an amendment, I would tell you. For right now, zoning systems or hydronic fan coils, plan on having a multi-speed fan on there. The demand for control ventilation rules, which have not changed at all since the 2012, they're exactly the same. I just bring them up because it is a very common controls-related topic in the code. If you have an occupancy density in this particular space that has more than 25 people per 1,000 square feet, you are very likely going to have to put a CO2 demand control ventilation system on there. That sounds scarier than it is. It's not hard to do that. All the Economizer controllers have an input waiting for this sensor. All you really have to do is buy the CO2 sensor, mount it on the wall, wire it to the rooftop or the Economizer controller on your split system or whatever you have. There are some exceptions when you don't have to do it, like really small systems, less than 1,200 CFM of outside air, or systems that have ERVs, because if you have an ERV, you're already kind of taking care of that outside air energy savings already in another way. So there's a few exceptions, but in general, plan on spaces with high density occupancy, such as classrooms, movie theaters, sports arenas. Plan on those spaces probably having to have CO2 sensors. Ben asks if the CO2 sensor can be in the return duct. That's an interesting question. So as far as the energy code is concerned, yes, it could. Sometimes other codes prohibit that. Off the top of my head, I know that LEED prohibits putting it in the return duct. I know that the state of Wisconsin rebate programs specifically prohibit it being put in the return duct. I know that I personally prohibit it putting it in the return duct. I hate putting it in the return duct. Theoretically, if you had a very simple system, let's say you had a school gymnasium and you had like 5 feet of duct and you just wanted to put in the return duct there, I would personally be okay with that. But as soon as you have a zoning system with VAV dampers or something like that, you definitely cannot put it in the return duct, right? Because I put it in the return duct, I'm sensing the average CO2 of all of these zones. And how can I start throttling back the airflow for specific zones if I don't know what's going on in those specific zones? So on a VAV system, you got to put on every single damper. Every damper for the spaces that require it. So that damper can be throttled back. And then from the main air handler's outside air damper, he needs to look back at the zone dampers and see where they're positioned in order to decide what he's got to do on the other side of the equation. So sometimes return air CO2 sensor may be prohibited. Sometimes it may be allowed, but even when it's allowed, it's probably not the best idea. People want to do it because they want to save first cost, but it really makes it impossible for you to throttle back the ventilation air. Dale asks, is the design OA based on IMC, or will the Chicago OA requirements also work as the go or no-go for DCV? The code that you would have to follow, Dale, would be whatever code is in the jurisdiction that you're in. So if you're in the city of Chicago, you got to follow the Chicago ventilation code. If you are in one of the suburbs, you're following probably the IMC and some specific version of the IMC. I will explain both of those codes here in a minute for everybody else, but whatever code, ventilation code you're following will dictate how much outside air you need. And then once you know how much outside air you're required to bring in by code, then you can look over here at exception number 3 on the screen and see if that applies to you or doesn't apply to you for the CO2 sensor. There are other demand ventilation systems that are now required by code as well, specifically ones for parking garages. Obviously, we wouldn't use CO2 sensors in this case. We would use carbon monoxide sensors for cars and nitrogen dioxide sensors for diesel vehicles, or some combination of those if I had a multi-use space. So in those cases, we have to have the ability to stage down or modulate fan airflow. There are some exceptions to that, such as exception number 1, really, really small garages. Well, even mediumly small garages, I guess, if that's a word, or garages that that do not have heating or cooling systems in them. So if it's an enclosed garage in Chicago, you're probably going to have to do this. If it's some wide open garage at Oak Brook Mall, you're probably not going to have to do this. But I'm just throwing it out there so you're aware of it, that there are code requirements for that now. Even without the code, you should have been doing it anyway because it's such a stupid payback. It's like 85% energy savings on the jobs that I've done in the past. It's ridiculously fast. So either way, you should have wanted to do it. All right, quiz question number 2. Let me launch it first, I guess. All dry bulb economizers in climate zone 5 are required. All right, my screen just fell asleep. That's not good. All dry bulb economizers in climate zone 5, which is Northern Illinois, are required to have which of the following? Please select one. A, occupancy interlock, fault detection, and CO2 sensor. B, occupancy interlock, fault detection, 70-degree dry bulb set point. C, fault detection and CO sensor. Or D, DDC controls. The key word really being all, right? So if you got an economizer and you're going to do dry bulb, which of these things do you have to do on all of those economizers? All right, 84% of people have answered. So I am going to close it in 5, 4, 3, 2, 1. Let's close that and let us share the results with you. So the correct answer, as most of you got, is B, occupancy interlocked, fault detection, and a 70-degree set point. The CO2 sensor is not required in all cases. CO sensor would never be required on an economizer, and DDC controls are not required. So the only answer would be B. All right, back to the slides. All right, so some other little quick hit topics to mention under the thermostats and control section. Got to have 7-day programmability. If you have thermostat and it's a quote-unquote 5+2, that does not count. It has to have 7 individual programmable days. Whether someone's going to use them or not, it's another debate, but that's what it has to have. You have to have the ability to set it back to 55 and 85 degrees. If the occupant chooses to change that later, that's fine, but you as the specifier or installer need to provide them that stat and set their setbacks for those numbers, and then whatever they do later on, that's their own thing. You have to have at least a 5-degree dead band. What does that mean? That means in the stat, you have to have it programmed, configured such that the heating and cooling set points are always forced to be 5 degrees apart from each other. So if you want to have 70-degree heating and 75 cooling, that is fine. If somebody goes up to the stat and bumps the cooling set point from 75 down to 73, it has to automatically force the heating set point from 70 down to 68 to maintain the 5-degree dead band in there. Lots of thermostats do that. They are typically defaulted to 2 degrees. You need to change them to 5. You got to retain the schedule for 10 hours of power loss. You could do that with a battery backup, but quite honestly, that's stupid. So don't do that. Do it that way. You're better off just any modern thermostat has double EEPROM chip in it, so it burns the settings in there. And if you lose power, it doesn't go away. But if you really want batteries, God bless you, put batteries in. You have to restrict the overlapping of heating and cooling set points, which sounds obvious because we just said you have to have a 5-degree deadband on the thermostat. But what about when you have 2 thermostats in the same room? Sometimes this happens. Sometimes you got a radiant floor in a perimeter office zone, and it's on its own thermostat, and then you have the air side cooling on a different thermostat. That's fine. You can do that, and I understand why you might want that because the radiant floor has different lag times and all that. But if you do that, you have to have something that interlocks these things, so at no point in time can the heat come on with the cooling. It can't be, oh, I told the building operator to never let them overlap. That's not good enough. It has to automatically prevent them from overlapping the heating and cooling set points so you can't simultaneously heat and cool. You have to have the ability to override the thermostat for up to 2 hours. Someone walks up to the thermostat, instead of putting it in the hold mode, if they push the buttons to increase or decrease the set point, it should override for just 2 hours, or give them the option of picking how many hours they want to override it for. Or you can put a motion occupancy type sensor in there and do it that way. That is also fine. You have to have intelligent start routines built into your thermostat or your DDC controls. There's lots of different names for those depending on the manufacturer of the stat, but they all work basically the same way. So if you tell the thermostat you're going to occupy your building at 8 a.m. tomorrow morning, normally someone would probably configure the stat and program it to turn on at 6 or 7 in the morning. Well, now you don't do that. You actually program the stat for 8 a.m. and the thermostat has to calculate how much earlier it should start to get to the desired set point by 8 o'clock. It looked at the previous day's worth history typically to do that. Some of them have routines to look at outside air also, but it has to have some mechanism to decide how long to take to heat or cool your structure and start your thermostat that many minutes early to get there at the exact time you want. Why does it save energy? Well, if I just told your stat to randomly start at 6:30 every morning, so at 8 o'clock everything's good, that's an hour and a half early every day. On a mild day, I may be able to start 20, 30 minutes early and get there in plenty of time. So by having it done automatically, I save incremental minutes each day times the course of the year. It pays off pretty good. Lots of thermostats are available with this technology. It's been around for 20 plus years, but you got to make sure you buy or specify one that does it and then enable the feature as well. It's typically defaulted off. And like I mentioned on the economizer discussion, something has to shut the outside air damper down in the middle of the night when nobody's there, or unoccupied period when nobody's there. Typically, that's going to probably have to be the thermostat or the DDC controller because there's nobody else that can shut it down automatically. So when you're picking a thermostat, pick one that has that output on it. Keep moving along. For the control side of the world, outside and exhaust dampers. You're required to have shutoff dampers, obviously, and now they have to be quote-unquote low-leak dampers. Low leak is specifically determined to be 4 CFM per square foot at 1 inch of pressure. Right, so that's what defines a low-leak damper. Typically for rooftop manufacturers or air handling manufacturers or damper manufacturers, if you tell me you need a quote-unquote low-leak damper, they know what that means. But if you want to be more detailed, you can specify a maximum of 4 CFM of leakage per square foot tested at 1 inch of pressure. You can use gravity dampers instead of motorized ones like the code says, but only for small buildings that are 2 stories and less than 300 CFM. So for most systems, you're going to have motorized dampers. That ensures a tight shutoff and hence less leakage. So if you're buying a rooftop, for example, you got an economizer already, so you already got a motorized damper. So you're probably fine if you order the low leak damper and economizer controller, you're there. If you have a built-up system, then you're going to have to pay more attention to this. Boiler outside air reset is mandatory. You have to do it. It's not optional. You cannot run your boiler at 180 degrees all year long. You need to reset it based on something. We'll talk about that in a little bit, but typically you're going to reset it based on outside air. The cooler it is outside, the warmer the air I want, or excuse me, the warmer the water I want, and then the warmer it gets outside, the cooler the water I can use. If you decide to put snow melt systems in, you have to have different controls on there to prevent it from wasting heat. So you have to shut off the system if the pavement gets above 50 degrees. So you got to have a pavement sensor. That requires some thought on your part because you have to install that before the concrete is poured. So you can't do this kind of after the fact when you hire the controls guy. You got to have that sensor put in when the guy pouring the concrete is there. You got the pavement's above 50 and there's no precipitation falling. So you have to have a sensor that senses moisture as well. And then also you have to have a shutoff if it's above 40 degrees of outdoor air temperature. So you got 3 different shutoffs that you have to have there on a snow melt system to prevent heating when it's not needed. Oops, what did I click on there? Oh, okay. If you're going to have freeze protection on pipes, right, heat trace tape on your pipes and stuff like that, you have to have an automatic control that disables them whenever it's 40 degrees, right? So the controls have to be wired up for that. It says, or when conditions are such the fluid will not freeze. That language is there to accommodate things that are not plain water. So if you have something with glycol, you might have a different setting. If you have a different unrelated fluid for some reason, you might have a different setting. But if it's just plain Jane non-glycol water, 40 degrees is your code required setting. If you decide you want to heat things outdoors, obviously you don't care about saving energy, but we're still going to try to force you to save a little bit. You have to use radiant heat. That is code required. I don't have it on the slides here because this is a controls topic, but you have to do it radiantly. That means tubing in the concrete or overhead infrared heaters. You cannot do any other method of heating. It has to be radiant-based heat. And from the control side of it, you have to have an occupancy sensor. So if you want to heat a beer garden with overhead infrared heaters and nobody's out there in the beer garden smoking and drinking, guess what? The sensor says nobody's there. We shut off the heater. Someone walks out there, we turn the heater back on. And then if you're going to have an ERV, whether it's code required or whether you chose to do it, either way, from the control side, we have to have bypass dampers that will allow airflow to go around the ERV wheel or heat exchanger to give us an economizer type function, right? So if it's an economizer day and I'm trying to get free cooling from outside and I run my ERV, guess what? I'm warming up that air with the ERV, which I don't want to do. I want free cooling. So I have to shut off the ERV and open up bypass dampers to directly allow that airflow to come around that heat exchanger. Hydronic systems, from a controls perspective, boilers and chillers, there's a few things that you definitely have to do as well. You have to have a means of automatic water temperature reset based on something. They give you lots of choices of the something. Zone valve positions is one such way. You can do it based on return water temperature. You can do it based on outside air. And there's a few other things they'll let you do as well. But you got to have something that resets the temperature so you're not always providing 45-degree water. Something has to bump it up to 46 or 47 or 48 or whatever it is. Systems that have 10 horsepower pumps and above, you have to have variable flow, variable speed drives basically. So from the control side, plan on controlling those. As soon as you have 10 horsepower pumping up, you should know in your bid, I need to have a VFD in there, or somebody does, and I got to control the VFD. If you have chiller plants or boiler plants that have more than one chiller or one boiler, I guess you're going to call it a plant, you probably have more than one, you have to have isolation valves that stop the flow of water from going through the machines that are off. It's obviously somewhat of an energy waste to do that. There are exceptions for that. If you have chillers in series, you don't have to do that, obviously. But if they're in parallel, you do need to shut off the flow to a chiller when it's not running. And then not only shut it off with the isolation valve, but then you also have to slow the flow down, probably based on a variable speed drive, right? If you have a two-pipe changeover system, first off, you're asking for trouble, but if you choose to do that and you tell your building owner, oh, we can only have heating, we can only have cooling, we can't have both, which is hard for lots of buildings, but if you do that, there's some specific rules that are required. You have to have an outdoor air temperature deadband of 15 degrees. That means if you tell people we're not turning the chiller on until it's 75 outside, that means the boiler has to come off at 60. And between 60 and 75, you're not allowed to run the chiller or the boiler. Right? So you have to have that deadband of outdoor air temperature where you're not running anything at all. You don't have to pick 60 and 75. You could pick 58 and 73 or whatever numbers you want, but 15 is a deadband, and that's a pretty big number. There's some other rules as well. Once you pick a mode, boiler or chiller, you have to run it for at least 4 hours before you're allowed to switch over to the other one. And you have to wait for the fluid temperature of the loop to cool down on its own before you switch between. And you got to let it cool down to within 30 degrees of the set point of the other mode that you want. So there's lots of rules that make it a little bit harder to do two-pipe systems, and it'll probably result in more occupant complaints than you already get on two-pipe systems. But if you want to do a two-pipe system, that's the rules. On the hydronic side, still from controls perspective, if you have a cooling tower or a dry cooler or something like that, plan on controlling fan speed on those. If you have 7.5 horsepower motors or larger, which is pretty big, but you'll definitely have cooling towers that have that. You can do it based on leaving water temperature if you choose. We at Carrier and TEC oftentimes prefer that you do it off of what we call the head pressure reference signal, which is what the code refers to as the condensing pressure and temperature signal. So the chiller basically tells the cooling tower when it needs less capacity, right? If you have a multi-cell cooling tower, you need to operate all the fans at the same speed as opposed to staging the fans. So in other words, let's just say, keep it simple, you have two fans. Instead of running one at 0 and one at 100%, you would run two at 50% or whatever flow you needed, right? If you had 8 of them, same kind of thing, you'd run them all at some lower capacity, and then only if you get down below the minimum that you can run them at, then can you start staging them off. There are some exceptions on that one, I believe, that if the manufacturer has a specific recommendation, you could follow that instead of this. But for the most part, you're going to ramp the fans down together, which is smarter because you get more surface area per airflow, so you should want to do that anyway. If you have a water source heat pump loop type project, like we have many of in the city of Chicago, similar to the two-pipe changeover systems, we have lots of rules on the temperatures and so forth. We're required to have a water temperature deadband of 20 degrees between the boiler and tower operation. So I can heat the loop up, let's say for argument, I can heat the loop up to 60 degrees with the boiler. I can cool the loop down to 80 degrees with the cooling tower. And between 60 and 80 degree water temperature, I am not allowed to run the boiler or the cooling tower. Now, I just picked 60 and 80 in my head. You could have picked 55 and 75. You could have picked 65 and 85. But there's some 20 degree temperature of water that I'm not going to be allowed to run the boiler or the tower. And then also you have to have a heat exchanger between the loop and the tower, which is not the controls problem. But on the control side, because that heat exchanger is there, we must stop the tower pump and close an isolation valve. So we're going to the heat exchanger instead of the tower, and someone's got to control that changeover scenario. All right, quiz question number 3. Which of the following is not, I repeat, not recommended on all, I repeat, all zoning systems with DX equipment 5 tons and up? So which of these do you not have to do all of the time? Choice 1, 3 stages of compression. Choice 2, economizer. 3, 2-speed supply fans. D, outside air. E, A, and C. While I'm waiting for you guys to answer, because you guys are kind of slow on this one, I'll read some questions. Ben asks, I believe California requires a pre-occupancy outside air flush out to remove VOCs, which is contrary to the OA dampers closed during morning warm-up in the IECC. Do you think the code may be changed in the future to incorporate a flush out? I know what you're talking about. We often did pre-occupancy purge when I was a control contractor. The code does not currently state that you can do that. I would imagine that if you need to do that or want to do that, or your ventilation code says you should do that, I'm going to bet that your permit reviewer and your inspector probably would work with you on that. But technically, as it stands right now, during the morning warm-up, you need to shut the damper. So it doesn't really accommodate for that per se. But I bet that's something you can get an exception to if you needed to for your project. Greg asks, does low leak MODs apply to toilet exhaust fans? Yes. Nothing, I'm going off the top of my head, I don't have the code in front of me at the moment, but nothing in there specifically excluded any types of exhaust fans. It just said outside and exhaust intakes and exiting holes needed to have low leak dampers. It didn't say there's an exception for something else. So I'm going to say yes. If we need a direct answer, Greg, we'll have to go back and read the code language specifically to make sure there's no exception in there. And then last one, then we'll go back to our question because only 78% of you voted so far. IEC 2015 requires Economizer for 54,000 BTUs. Do you know what is the requirement per City of Chicago Energy Code? I believe off the top of my head, the City of Chicago Energy Code is still using, in their written code, is still using 33,000 BTUs, but I don't know that as a fact. I would have to look that up. I'm not positive, Anwar. All right, so I'm closing this question thing in 5, 4, 3, 2, 1. And I can tell based on the answers and how long it took people and the fact that only 86% answered that I must have written the question in a way that was hard. So you can see on the screen there. So the question is, which of the following is not required on all zoning systems 5 tons and up? So 3 stages of compression is required on all zoning systems. Economizer for that size system is required. 2-speed fans is required. Outside air reset is not required. So the correct answer is 25% D, outside air reset. Most people did not get that correct, so I think maybe I got everyone confused with the not and the all words. That's the only I could think of there. All right, because I like the questions. Question number 4, we'll do it right now. Which of the following are not mentioned in the IEC 2015 code? Not. Follow the not, please. Economizer, snow melt control, variable frequency drives, duct smoke detectors, or all of the above. And I'm not being literal here with the words, like the concept. Is it the concept of an economizer or the concept of VFD addressed in this code? So don't take it too literally. Greg says I didn't post the question. Sorry about that. I guess that would help. I'm like, no one's answering. So which of these are not something that's addressed in the energy code? Hopefully this one's a lot easier than the last one and we'll make up for that last one being a tough one. All right, 80-some% of the people have answered, and so far everyone's answered it correctly, so you guys are doing awesome. So I'm going to close it in 5, 4, 3, 2, 1, and the correct answer is D, duct smoke detector. All right, moving on. I'm going to power through some of these, get caught up a little bit. By the way, when I send you guys the PDA certificates, I will send it for 1.5 hours. I think we only said 1 on the screen, if I recall, but it's going to be like 1 hour and 25 minutes, so that's basically 1.5 hours. So just keep that in mind too. So don't feel bad that we're still talking here. All right, VAV controls. There's lots of rules of VAV controls. I'll try to highlight them for you guys that specify buy or install VAV systems. The first one, which is an interesting rule, is that we used to always locate the VAV static pressure sensor 2/3 down the duct. Why do we put it there? Because we've always put it there, right? No particular reason. We knew that we'd get a decent average down there, get it close to the control zone. In the perfect world, what we do is we'd measure the pressure drop across the worst VAV box and we'd control down by that. But we don't know what that is typically in the control side, so we just put it 2/3 down and kind of said, great. Now the code is such that you have to locate the duct static pressure sensor somewhere that is 1.2 inches or lower of a set point, right? So if I have to run the system at 1.5 inches in order to get airflow to make the balancer happy, guess what? I got to put the static pressure sensor further downstream now than that because that was only 1.5. I can keep moving down the duct till I have less static pressure that gets me what I need for CFM. So that's something to keep in mind. The 2/3 rule is now gone. You probably have to locate it further down, and you may have to have multiple sensors on multiple branches to get this accomplished. If you have DDC controls on your VAV system, and let's face it, almost everybody has DDC controls on their VAV system. Hardly anybody uses pneumatics other than some old hospitals. But as soon as you put DDC controls in, there's lots more code things that kick in. They don't make you do it on pneumatics because pneumatics is completely inflexible and obviously not possible to do most of these things realistically. So you have to have the set points for VAV systems automatically reset. So yeah, I'm controlling the 1.2 inches of static in the duct there, but I have to be able to reduce that as zones don't need air. A common routine would be, we call this static pressure reset. A common routine would be if I look at all my VAV boxes, and by I mean the computer, if the computer looks at all the VAV boxes and nobody's open more than say 80%, obviously I'm providing you too much air because nobody wants all of the air, everybody's throttling back. Therefore, I should reduce your static pressure set point from 1.2 inches down to 1.1 or whatever it was. And I'll keep reducing that until somebody's open like 95% or something like that. Then I'll stop doing that. right? And then if somebody gets closer to 100% open, I'll say, oh, they must want more air, and I'll start bumping the set point back up. You have to do this automatically. Automatically means without human intervention, right? On small systems, on a VAV system, small fans, specifically between 1/12 horsepower and 1 horsepower, you have to use an ECM motor, right, for either direct controllability or for balancing purposes, but you have to have that more efficient ECM motor in there. And specifically, the interesting note is motors in the airstream within fan coils and terminal units that only provide heating to the space served, right? So that has been lately being interpreted as if you have a parallel fan-powered box that provides heating to the space served, you don't have to do the ECM motor. If you have a series fan-powered box, it is running for both heating and cooling modes, and hence it does have to have an ECM motor. So that's the way we've been kind of looking at that one thus far. So ECM motors on series fan-powered boxes, as well as for fan coils. You have to do supply air temperature reset on VAV systems, right? This basically means you can't run it at 55-degree discharge air all the time. You have to reset it to 25% of the difference between the supply air and the room temperature. So if you have a 55-degree supply air design and you have a 75-degree room temperature, 25% of that would be 5 degrees. Therefore, I have to be able to reset your supply air temperature between 55 and 60 degrees. And depending on what the spaces want, I can go between those two things. You can do that based on building load, which typically means let's look at all the zone temperature readings and see how close they are to their set points. Or you can do it based on something more indirect, like outdoor air temperature, which I would not recommend, but it is allowed by code. I would highly recommend you do it based on what the zones are asking for. But if you have multiple zone VAV systems, or VVT systems for that matter, you cannot provide a constant discharge air temperature. You need to reset that from 55 to 60 degrees, or some version of that. There's an exception there for systems that prevent reheating, recooling, or mixing of heated and cooled supply air. If you have a hot water coil, if you have an electric heater, if you have a fan-powered box, anywhere on your VAV system, even if it's just one zone, you can't use that exception. If you had a 100% cooling-only system and there's no possible source of heat at any of the zones, then that would be fine. You wouldn't have to do this reset because obviously you're in a place that needs cooling all the time. You're in some very hot place like Qatar or something like that. So that's kind of the deal on those. This one's been in here for a very long time. People still don't understand it. There are rules that prevent you from reheating air. And by the way, if you heat air that came from the quote-unquote cooling economizer, that is still counted as reheating it. So it does allow reheat for VAV systems. So you can't like take a hot deck and a cold deck and mix them anymore and like that. But if you have reheat on a VAV system, you're allowed to run the reheat even when the air handler is in economizer or in cooling mode. If you follow certain rules, the big noted rule on that from a control standpoint is you have to first throttle the CFM of that particular VAV box down to 30% of its maximum design airflow. Then you can start opening the hot water valve or staging electric heater. And then if you need to, especially with electric heat, you could start increasing the CFM to keep the heaters online if you had to. But you first got to throttle everything back. I want to keep trucking along to keep moving here. I'm going to skip a few of these slides. You guys know we have ventilation codes. You know we've had them for a long time. They used to be based on a per person basis. As of 2004, ASHRAE Standard 62 Addendum N, we switched it from a per person basis to a per person and a square foot basis. And the main reason of that was to allow us to ventilate differently for people versus spaces, right? The two reasons we ventilate a space are people. People basically stink and they bring germs in the building with them, and you need to dilute them down. And then the building itself, the paint, the furnishings, the carpeting, whatever, is giving off VOCs, and we need to dilute those down. So now, as of 2004, we're allowed to take care of the people-based and the space-based pollutants separately with the ventilation rates. So from a controls perspective, what you really need to know is that it's a per person plus a per square foot number that equals the total. The controls designer is probably not the one doing this, right? The mechanical designer is, and they're just giving you the number saying, oh, we need this much air, we need this much air, we need this much air for these different air handlers, right? Where it comes into play for you on the control side as a controls designer is now that ASHRAE has separated these into two different numbers, and you can see here I highlighted an office space. requires 5 CFM per person plus 0.06 CFM per square foot, whereas the old standard, 12 plus years ago, was just 20 CFM per person total. Right now that's in 2 separate pieces. It was done that way specifically to allow us to do things like demand control ventilation. I can now modulate this 5 CFM per person part and still maintain the 0.06 constant times square footage and allow me to modulate the ventilation air back as the CO2 levels change. So that's a specific reason for separating these. There may be other reasons, but in 12 years, nobody can tell me any other reason we separated other than for CO2 demand-based control ventilation. Somebody asked about Chicago Mechanical Code. As you know, the Chicago Mechanical Code is different than the ventilation code everywhere else in the world. The city of Chicago and the state of Wisconsin seem to be the only places doing their own thing as far as the ventilation rates. Everybody else is following ASHRAE 62.1, or they're following the IMC, and both of those have basically the same table for the most part, and the tables have been the same for 12 years for the most part. So City of Chicago and the state of Wisconsin are a little bit unique. City of Chicago does not tell you how much outside air to bring into particular spaces. It tells you how much supply air to bring into particular spaces. And for that same office example we were just looking at, it says bring in 0.6 CFM of supply air into that space, even if that space doesn't need that much CFM to cool it needed. That's what you got to design it for. Bring it in for that. And then in a different section of the code, it specifically says whatever supply air you bring to the space, at least 33 1/3% of that has to come from outside, right? So for the case of an office building, if we pull up our little calculator and we say 0.6 times 0.33, I got to bring in 0.2 CFM per square foot of outside air into an office building in the city of Chicago. 0.2 is a pretty high number. Wisconsin is the opposite. Wisconsin says we don't care about the square footage at all. We want 7.5 CFM per person as a flat rate for all of our spaces. So Wisconsin, there's hardly any outside air requirement. Chicago, there's the most of anywhere, and everybody else is in the middle. But just kind of keep that in mind. The mechanical designer should be dictating to the controls designer how much outside air he needs to bring in, and the controls guy will then want to take that and decide how much he can modulate. So you kind of need to understand how this table works right here to know which part you can modulate. You can modulate the 5 CFM per person part. You cannot modulate the 0.06 CFM per square foot part. So the mechanical code in ASHRAE 62 specifically allows CO2-based demand control ventilation, and they have done so for over a decade. It specifically spells it out by name in the code language. So you can do this. You can throttle back the outside air level when people are not there and breathing. And the CO2 sensor is an indicator of who's breathing. City of Chicago, in regards to CO2, is actually ahead of the curve, and they came out with their language in their mechanical code to allow CO2 a year before the rest of the country did. City of Chicago does it a little bit differently, though. And instead of letting you kind of, as an engineer, decide what the set point should be, they give you a fixed set point of 1,000 parts per million that you cannot go above in the space. And then the last thing on the CO2 discussion comes up on LEED type projects. One of the indoor air quality points that you can achieve in the LEED standards can be achieved by doing carbon dioxide monitoring in the space. As I mentioned before, you are not allowed to do it in the return duct. It has to be in the space. Specifically, it has to be between 3 and 6 feet above the floor. I suppose if your return duct was on the wall at 5 feet, I guess you could probably get away with saying that, but generally speaking, it's got to be wall mounted. And then you have to have a way to alert or alarm the people if the CO2 level increases above a threshold. So you're probably doing CO2 by code in those spaces anyway, so to have it help you get the LEED point, all the easier. All right, quiz question number 5. As we're coming down the home stretch here, last few slides. All right, so the question is, carbon dioxide sensors for demand control ventilation are required or allowed by which of the following? Required or allowed by which of the following? Your choices will be the IECC 2015, is it required or allowed? 62.1, required or allowed? IMC 2015, required or allowed? Chicago codes, required or allowed? E, all of those above. So who requires them or who allows them? I'll see if I can answer any other questions while you guys are clicking on that. Ken asks, does this require boxes to be linked or can you have standalone systems? Ken, let me know which topic you were asking that question on, and then I'll try to answer that. Dale asks, does Chicago vent requirement always trump ASHRAE 62.1? Ventilation effectiveness, etc. for lead projects seems to usually up the requirement above 62 levels, above Chicago code levels. Okay, so Dale's question basically is, do I have to follow the City of Chicago ventilation code or I have to follow ASHRAE 62.1 ventilation? For a normal project in the City of Chicago, you have to follow Chicago ventilation code. You do not have to follow ASHRAE 62.1 unless you choose to. However, if you were to do a LEED project in the City of Chicago, you would have to comply with both. The city's code has to be complied with, obviously, and then LEED, because 62.1 is a prerequisite to even get a LEED building built, you have to comply with that. So you would look at the two tables, figure out which one required more outside air than the other, and whichever one was the higher number, you would have to use that. Generally, my bet is that in most projects, it's probably going to be the Chicago ventilation code. That'll be the higher number. Ken's other question we asked before, when requiring duct pressure reset on VAV systems, does this require the boxes to be linked? So let's go back to his question real quick, and then we'll do the number 5 thing. So this is the one you were talking about here for duct static pressure reset. It is only required with direct digital controls of the zones. Now, when you say is it required they be linked, I guess in my world, as soon as you put DDC controls in, you're linking them. Like, I don't know why you would do anything that would be different than that. You're basically, if you say standalone DDC, that means you're not going to run a cable between stuff. Most of the code required things we're talking about, including some of these boiler resets and all that stuff, you got to link all the DDC controllers or you're not going to do half of this stuff. So yes, it requires they be linked because you have to look at all of the zones. If you don't want to link your VAV box controls and not comply with this measure, then you need to use pneumatic controls. But as soon as you put digital controls in, you have to do this. And in order to do this, you're going to have the zones communicating to each other and sharing information and data, basically telling the main air handler what they need for static pressure control. All right, back to our question, number 5, which I will close the polling on. 94% of you got the correct answer, which is all of the above. All of those things either allow it or require it. IECC 2015 requires it. ASHRAE 62.1 and IMC 2015 allow it. City of Chicago code sometimes requires it on the energy code side and sometimes allows it on the mechanical code side. So all of the above. All right, last couple things here. All right, ASHRAE 15, which is refrigerant safety standard. There is, in my mind, one thing that directly relates to the controls guys over and over again, which is that if you have an indoor refrigeration room, such as a chiller room, which comes up a lot, right? Or I guess a supermarket area, compressor deck or something like that. But we'll talk about it as a chiller room. You have to have a refrigerant monitoring sensing system. You have to audibly and visually alarm inside the room and outside every single door to the room based on the TLV, TWA numbers, which typically means 8-hour work week or 8-hour work day or 40-hour work week level. If you are in the City of Chicago, the language is completely different in the code, but it basically says the same exact thing, which means you have to have an audible and visual alarm outside every single door to the room, the building. All right, so basically it ends up telling you to do the same thing as far as the controls are concerned. There's other stuff that's different, but controls-wise, have alarms inside the building or inside the space and outside the doors to that space. These are the levels that we typically are looking at. So the TWA number we're looking at, or also referred to as 1/4 of the OEL number, typically is 250 parts per million. If we get to 250 parts per million of nowadays 134A or 410A, or even on the older refrigerants 22 or 12, if I get up to that number, I need to generate alarming. We typically have a secondary alarm. For this particular scenario, it's not going to really make a difference. I'm going to alarm at the 250, and hopefully everybody gets out of there and realizes that. But we do have a secondary alarm for lots of gas detection systems, and typically it ends up being double the primary. You need to locate the sensors 1 foot above the floor. That is because refrigerant is much denser than air and will sink to the floor first. So you need to alarm there first, measure it the first place it's probably going to end up. And most manufacturers of sensors will tell you they got about a 20-foot radius of detection to pick up these gases. So that usually all boils down to is a mechanical room that looks like this. I typically end up with 1 sensor per chiller. I suppose, you can make some arguments that I could probably have done this job with maybe 2 or 3 sensors, right? I could have put this one right here and had it cover both chiller number 2 and chiller number 3, you could have done that, I suppose. I typically have always done one sensor per chiller. My thought has been, you're buying a chiller that costs $100,000. We're not going to buy an extra sensor, really. We're not going to do that. And my thought has always been, well, this right now, what does that say? It's a 123 chiller, which if you saw on the previous page had a 12-part per limit. But if I change that chiller out to a new one later, it's going to have a different requirement. So maybe I'll end up with a 123 chiller here, but I'll end up with a 134A chiller there. Right? So then I can't do it with one sensor because typically it's one sensor per gas. So I'm going to have 2 sensors anyway, so I might as well wire it and set it up and put the conduit in for this scenario. So typically one sensor per machine, a panel on the interior section of that room that has a visual blinking alarm with strobe lights and an audible siren alarm. And then outside each door, I need to do the same thing. I don't have to have a panel per se, but I have to have the strobe light and the sounding horn. And a lot of times that gets accomplished with another panel. They're all interlocked together, so all of them are always alarming at the same time. Last few couple notes. Overhead heating systems, you probably heard me complain about this in every single class I've ever taught. If you've ever been to a Dan Inhouse class, you probably heard him complaining about it. This has been in the ASHRAE handbook for literally decades, and it made it into ASHRAE 62.1, I don't even know, 12 or 14 years ago. Basically, what ends up happening, if you have an overhead heating system like you'd have on an office with a VAV or something like that, you cannot have the discharge air temperature be any more than 15 degrees above the space temperature. If you do that, a bunch of rules kick in. The big major rule there is in ASHRAE 62, it'll require you to add 25% outside air to whatever CFM you're supposed to bring into the building. It gives it a ventilation effectiveness of a 0.8 instead of the default of 1.0 like overhead cooling would have, which the math ends up telling you have to bring in 25% more outside air. So don't let the air discharge get really warm coming overhead. Keep it below 90 degrees. I've told some of you guys before, I used to go to jobs as a controls contractor, especially on rooftop jobs, and I used to literally take my snips out and cut the second stage of heating wiring because the people in the space were saying that they were too cold. So I would disable second stage heat. Because if it's too hot, it hugs the ceiling and it goes right back out the return. The thermostat always gets exactly what it wants. It's always going to be 73 degrees or whatever you set it for. But the ceiling is going to be 102 and the floor is going to be 51 and people are going to be pissed. So the cooler discharge air actually lets the diffusers do their job, which is mix the air and throw it into the space, which means I get more uniform temperature between ceiling and floor, which means less people are upset, and I don't have to take a penalty on the outside air requirement. So keep the discharge air below 90 or probably below 85. If you're only heating it to 70 degrees, your maximum discharge air would be 85. Babysit the relative humidity in the space. ASHRAE 62.1 requires a maximum of 65% relative humidity in the space. You're not allowed to go higher than that. I typically recommend controls guys maintain it below 60 and alarm it at 65. ASHRAE 55 does not give you a specific defined number. It gives you the comfort graphical method. But generally speaking, if you keep that 65% number in mind, the graphical method usually will fall in line with that also. So control it to 60, alarm it at 65. There is no lower end relative humidity specified in any of the standards anymore. Those were all removed. So if you're really excited about humidifiers, there's no code reason to ever put a humidifier in, but there's obviously applications where it is needed, like a library or something like that. Not going to spend any time on electrical code other than 2 comments that always seem to ding the controls guys. In the city of Chicago, specifically, low voltage wiring in the plenum ceiling has to be in conduit. Nowhere else in the world does it seem to be required that way, but in the city of Chicago, if you want to run 24-volt control wiring through the ceiling cavity, you have to put it in conduit. It's not a big deal. It's not hard to do, but it does change how you bid the labor on your project. Additionally, you can't have any exposed wiring in the plenum, obviously, so your VAV controller hanging on the side of the VAV box can't just hang on the side of the VAV box like we do in every other city. It's got to be in a NEMA enclosure, right? It's got to be an electrical enclosure also. Duct smoke detectors typically fall under the controls guys a lot. Sometimes the mechanical provides them, sometimes the controls provides them, sometimes the fire protection contractor provides them, but somebody's got to provide them. The International Mechanical Code requires duct smoke detectors in the return duct whenever it is 2,000 CFM or larger system. NFPA requires it on the supply duct whenever it's 2,000 CFM or larger. If you are in a jurisdiction that is following both NFPA and IMC, then guess what? You got to put one in the supply and in the return. You got to do both. And then both of those codes require dual monitoring, return and supply, anytime it's above 15,000 CFM. So plan on providing at least one smoke detector, if not two, on every air handler. It's going to come up a lot. All right, our last quiz question. A chiller room with 2 entry doors will require how many audible, visual, and alarming stations? So the chiller room with 2 exterior doors, how many alarm stations do we have to have? 0, 1, 2, 3, or 4? Wow, and you guys are already all over the board on the answering it. See if there's a question I can answer. I'm caught up on all the questions, I think. So I'll let you guys vote on this, then I'll take any final questions, and then we'll get wrapped up here. So if you have any final questions, please type them in the chat box, and I will do my best to try to answer them. 76% of the people have answered. We'll give it a couple more here to get the last few people in, especially the ones that want their PDHs. All right, I'm going to close it in 5, 4, 3, 2, and 1. And the correct answer is actually 3. A lot of you guys have picked 2. I must have written that one in a tricky way also. If I have 2 entry doors, I need 2 extra monitoring sensors, or monitoring stations, alarming stations. I also need the one that's inside the room for the people in the room still, right? So just to be clear, since a lot of guys got this one wrong, so this exact drawing we had right here. I have 2 doors, 1. Oops, need my John Madden pen. Come on, John. Oh, John Madden pen's broken. The world's gonna end. Last chance for the Madden pen. All right, forget it. I'll just have to tell you where it's at, right? So 1 by the door on the left-hand side of the screen, 1 by the door on the right-hand side of the screen, and 1 in the room as well, top left-hand. So I have to have 3 monitoring stations for 2 doors, 3 alarming stations, excuse me, for 2 doors. Oh, that's why I couldn't use my pen, because I didn't take the screen down. Now I can use my pen. So door number 1, alarm number 1. Door number 2, alarm number 2. Alarm number 3 inside the room. All right, that's where the 3 comes from. So 2 entry doors, 3 alarming stations. Okay, so we are concluded, unless anybody has any other questions, which, see if anybody did. Greg says, might be worth noting that vestibule heaters require interlock with OA to shut down when OA rises above 45. I did not notice that in there. I'm not saying it's not true, Greg. It probably is. I'll have to research that one to see if the vestibule has to have an outside air interlock. Brian asks if this particular training was a lead continuing education units. No, it does not. It is PDHs for Illinois and Wisconsin is what it's pre-approved for. All right, any other questions from anybody? I don't see any more coming in. If you have other ones, send me an email or give me a call, and I will do my best to answer them. And I thank you guys for logging in. For anybody who checked the box saying that they were a PE, and if you also answered whatever it was, 4 of the 6 questions correct, you will get a certificate in about a week or so for 1.5 PDH hours. All right, and with that, I'm going to close it down. Thank you guys for your time.